A taxi driver in Greece retired his Mercedes diesel in 2004 after 46 years of daily service. The odometer showed 2.9 million miles on the original engine. No rebuild, no replacement, just regular maintenance and the same engine from 1976. Meanwhile, right now, thousands of frustrated owners are staring at repair bills for engines that failed before reaching 80,000 miles. Brand new cars, perfect maintenance records, dead engines. How did we go from engines lasting nearly 3 million miles to engines barely surviving their warranty period? The answer involves corporate greed, hidden engineering decisions, and a philosophy that treats your wallet as the ultimate target. Today I'm exposing 12 reasons why old engines refuse to die while new ones are designed to fail. The Great Betrayal. Before we dive into these reasons, let me tell you a story that explains everything about how we got here. In 1983, a young engineer at Mercedes-Benz proposed making the OM617 diesel engine block slightly thinner to save manufacturing costs. His proposal was rejected immediately. The senior engineer told him something that would never be said in a modern boardroom. "We don't build engines for accountants. We build engines for generations." That philosophy created the engine in that Greek taxi. Engineers measured success by how many decades their creations survived, not by how cheaply they could be manufactured. Something changed in the 1990s. Finance departments gained control over engineering decisions. Success metrics shifted from "how long will this last" to "will this survive the warranty period?" The 12 reasons I'm about to reveal aren't engineering failures. They're deliberate choices that prioritize manufacturer profits over your engine's lifespan. Each one chips away at the legendary durability that once defined automotive excellence. Let's start with reason number 12. Reason number 12, cast iron blocks built like bank vaults. The cast iron block in a 1985 Mercedes diesel weighed nearly 400 pounds by itself. You could drop it off a truck, scratch the paint, and bolt it right back into service. These blocks didn't crack. They didn't warp. They survived abuse that would destroy modern engines within months. That Greek taxi driver's engine lasted 2.9 million miles because cast iron handles heat like nothing else in automotive engineering. It expands and contracts evenly across thousands of thermal cycles. The cylinder walls could be machined larger 3 or 4 times during rebuilds, essentially giving one engine 4 complete lifetimes of service. Now look at what replaced it. Modern aluminum blocks weigh half as much and save manufacturers roughly $200 per engine in material and shipping costs. But aluminum expands at twice the rate of iron when heated. It requires pressed-in iron sleeves for cylinder walls, sleeves that can shift, crack, or lose their press fit over time and miles. When a modern aluminum block fails, there's no rebuilding it. The entire engine becomes expensive scrap metal. That $200 manufacturing savings transforms into a $6,000 engine replacement for the unlucky owner. The legendary engines weren't built with exotic technology or magic materials. They were simply built with materials chosen for durability instead of cost savings. And that single difference separates engines lasting millions of miles from engines dying at 80,000 miles. Reason number 11, cylinder walls thick enough to rebuild forever. Here's something most modern car owners never learn, because it no longer applies to their vehicles. Old engines were designed with rebuildability as a core engineering requirement from the very beginning. Open a service manual for a 1980s Toyota Land Cruiser, and you'll find specifications for 4 different overbore sizes. The factory expected these engines to be machined larger, fitted with fresh pistons, and returned to service multiple times throughout their operational lives. Machine shops across every country built entire businesses around breathing new life into worn engines. A typical rebuild costs $2,500 and return the engine to factory-fresh specifications for another 200,000 miles of reliable service. Perform that rebuild 3 times, and you've got an engine lasting 800,000 miles for less than the cost of one modern engine replacement. Modern engines have cylinder walls so thin that rebuilding is often mechanically impossible. There's literally not enough metal remaining to machine away safely. When these engines develop bore wear or cylinder scoring, the only option is complete replacement at cost ranging from $5,000 to $12,000 depending on the vehicle. This transformation wasn't accidental or unavoidable. Manufacturers discovered that selling replacement engines in new vehicles generates far more profit than designing engines that independent shops can rebuild affordably. They engineered away the affordable repair option entirely. That's not engineering progress. That's engineering betrayal disguised as innovation. Reason number 10. Oil change intervals that actually protected engines. Your grandfather religiously changed his oil every 3,000 miles, and his engine lasted 300,000 miles without burning a single drop. Modern manufacturers now tell you that 15,000 miles or even 20,000 miles between changes is perfectly acceptable for your sophisticated new engine. Those old engines with conservative oil change intervals rarely develop sludge problems throughout their entire lives. The oil simply never had enough time to break down, accumulate corrosive acids, or deposit varnish in critical areas like piston ring grooves. Fresh oil continuously protected bearings, rings, and valve train components from the wear that eventually kills every engine. Modern extended intervals exist primarily for one reason: marketing advantage. When manufacturers advertise lower cost of ownership figures, fewer required oil changes make their numbers look dramatically better against competitors on comparison sheets. The uncomfortable fact that extended intervals accelerate long-term wear doesn't appear in warranty statistics because most serious damage surfaces conveniently after coverage expires. Oil sitting in an engine for 20,000 miles absorbs combustion acids, loses its viscosity stability, and allows harmful deposits to form in piston ring grooves where they cause the most damage. By the time oil consumption and symptoms become noticeable, the internal damage is permanent and completely irreversible. That 2.9 million mile Mercedes taxi? The owner changed oil every 3,000 miles without exception for 46 consecutive years. Conservative maintenance isn't paranoia. It's how ordinary engines become extraordinary legends. Reason number 9. Turbochargers on engines that never needed them. Walk through any modern dealership and you'll find turbochargers bolted onto everything from basic economy hatchbacks to family sedans and crossovers. Manufacturers call this strategy downsizing, using smaller engines with forced induction to match the power of larger naturally aspirated engines while meeting strict fuel economy regulations. Here's what the glossy marketing materials conveniently forget to mention about this engineering trade-off. A naturally aspirated 3.0-liter engine making 200 horsepower operates at roughly 40% of its maximum capacity during normal daily driving. There's enormous margin for error, abuse tolerance, and long-term longevity built into every single component. A turbocharged 1.5-liter engine making the same 200 horsepower operates near 80% capacity during every highway merge, every hill climb, every passing maneuver. The engine is constantly stressed dangerously close to its absolute design limits. Turbochargers spin at speeds exceeding 150,000 RPM and reach temperatures over 1,800 degrees Fahrenheit during normal operation. They demand perfect oil quality, precise cooling system function, and careful shutdown procedures to survive their intended lifespan. Modern economy car buyers have absolutely no idea their small turbocharged engine requires more careful treatment than their parents' larger naturally aspirated engines ever needed. They follow extended service intervals religiously, shut off hot engines immediately after hard driving, and wonder why their turbo fails catastrophically at 60,000 miles. Old turbo cars came with owner education. Modern turbo cars come with future repair bills. Reason number 8, timing chains that were actually lifetime components. Here's a question that reveals everything about modern engine design philosophy. Why would a component specifically advertised as lifetime regularly fail before reaching 100,000 miles? 30 years ago, timing chains were genuinely lifetime components worthy of that marketing description. The chains used heavy-gauge steel links built for decades of service. Guides were machined from solid metal. Tensioners used robust mechanical systems that operated independently of oil pressure. Engineers designed these systems to outlast the engines themselves because timing failure meant complete catastrophic engine destruction. Modern timing chains tell a completely different and far more expensive story. Visit any automotive forum and you'll find thousands of frustrated owners reporting stretched chains, shattered plastic guides, and failed tensioners at mileages that old engines considered barely broken in. The chains became thinner to reduce rotating mass and manufacturing costs. Metal guides became cheap plastic to cut expenses further. Mechanical tensioners became hydraulic units entirely dependent on oil pressure through tiny passages that clog when owners follow those manufacturer-recommended extended oil change intervals. In 2019, a major manufacturer faced a class action lawsuit over timing chain failures, affecting hundreds of thousands of vehicles with average failure mileage around 80,000 miles. Owners received partial settlements, but still faced repair bills exceeding $3,000 for components that were marketed as completely maintenance-free. The old timing chains weren't overbuilt by accident. Modern timing chains aren't underbuilt by accident either. Reason number 7, direct injection, creating problems that never existed before. Let me explain why your parents' cars never required a maintenance service that modern vehicles desperately need every 50,000 miles just to keep running properly. Traditional port fuel injection sprayed gasoline directly onto intake valve surfaces before fuel entered the combustion chamber. This continuous fuel wash naturally cleaned carbon deposits with every single engine cycle throughout the engine's entire life. Valves stayed perfectly clean for hundreds of thousands of miles without any special maintenance intervention whatsoever. Direct injection technology sprays fuel directly into the combustion cylinder itself, completely bypassing intake valves entirely. Without fuel continuously washing over them, carbon deposits from crankcase ventilation vapors accumulate steadily on valve stems and seating surfaces with every mile driven. By 60,000 miles, some engines develop carbon buildup severe enough to cause misfires, rough idle conditions, and noticeable power loss. The required cleaning procedure, called walnut blasting, costs between $400 and $800 and must be repeated every 50,000 to 60,000 miles for the engine's entire remaining life. Manufacturers conveniently don't include this essential service in published maintenance schedules, leaving owners to discover the expensive problem through drivability complaints and illuminated check engine lights. A 2021 automotive industry study found that 67% of direct injection vehicle owners were completely unaware their engines required periodic carbon cleaning until symptoms became severe enough to notice. Old port injection simply worked forever. Modern direct injection creates permanent maintenance requirements. Reason number 6. Piston rings designed for efficiency, not longevity. The corporate obsession with fuel economy ratings has driven engineers to eliminate friction from every possible source inside modern engines. One area where they found significant friction reduction was piston ring design. And this particular decision is destroying engines earlier than ever before in automotive history. Old engines used thick, robust piston rings that sealed cylinders completely under virtually any operating condition imaginable. These rings could handle dirty oil, extended intervals, cold starts, and significant owner neglect without ever losing their ability to control oil consumption and maintain proper compression. Modern low-tension rings are precision components operating at the absolute razor edge of their design limits continuously. They require perfectly clean oil change at proper intervals, engines reaching full operating temperature before being worked hard, and manufacturing tolerances measured in 10,000ths of an inch. Any deviation from these ideal conditions accelerates wear dramatically. When modern piston rings fail, the symptoms progress predictably and expensively. Oil consumption that increases noticeably every month. Blue smoke on cold morning starts, then complete sealing failure requiring engine rebuild or total replacement. Repairs typically cost $4,000 to $8,000 depending on the vehicle and labor market. That legendary Greek taxi used thick, heavy piston rings designed for decades of punishing taxi service. 2.9 million miles of service, to be precise. Modern rings are designed for warranty period survival and impressive fuel economy numbers, while long-term durability becomes someone else's expensive problem. Reason number 5. Components you could actually replace individually. Picture a mechanic working on a 1988 Toyota pickup truck with 400,000 hard miles showing on the odometer. The water pump is leaking coolant. He unbolts 4 simple bolts, removes the old pump, installs a $45 replacement from the parts store, and the truck runs reliably for another 100,000 miles. Total repair time, 1 hour. Total cost, including labor, under $150. Now picture the identical repair scenario on a modern vehicle. The water pump is integrated into the timing cover assembly, driven internally by the timing chain, and requires removing the entire front of the engine just to access it. That simple $45 water pump becomes a $1,200 repair bill, because the entire integrated assembly must be replaced together as one expensive unit. This integration trend isn't about better engineering or improved reliability. It's about faster assembly line installation times that transfer all future costs from manufacturer to owner. When any single component within an integrated assembly fails, the entire unit requires expensive replacement regardless of which specific part actually caused the problem. Modern vehicles feature thermostats permanently molded into plastic coolant housing with integrated sensors. Oil pumps driven by timing chains instead of separate accessible external drives. Alternators buried beneath intake manifolds requiring hours of expensive disassembly just to reach them. Old engines were designed for mechanics to repair affordably. Modern engines are designed for accountants to maximize profits. Reason number 4, cylinder deactivation, creating unexpected problems. Here's a fuel-saving technology that sounded absolutely brilliant in corporate engineering presentations, but creates real-world problems that nobody fully anticipated before millions of vehicles were already on the road. Cylinder deactivation shuts down half your engine's cylinders during light load highway cruising to theoretically save fuel. On paper and in presentations, this seems like engineering genius. Why burn expensive fuel in cylinders you don't actually need at that moment? In real-world daily operation, cylinder deactivation creates unique problems that engineers are still desperately trying to solve years after widespread implementation. When cylinders deactivate, combustion stops entirely, but pistons continue moving up and down inside the bores. Without combustion pressure pressing rings firmly against cylinder walls, oil that should be scraped back down instead slips past the rings and enters the combustion chamber above. When those deactivated cylinders suddenly reactivate, they burn the accumulated oil that collected during deactivation. Owners notice oil consumption that seems completely excessive for a supposedly modern, efficient engine, sometimes reaching 1 quart every 1,500 miles or even worse. Multiple major manufacturers have faced expensive class action lawsuits over excessive oil consumption, directly linked to cylinder deactivation system design flaws. Settlement terms typically provide partial reimbursement for affected owners, but don't cover the ongoing frustration and inconvenience. Old engines kept all cylinders firing continuously all the time. Boring perhaps, but they also didn't require class action lawsuits to address fundamental design problems. Reason number 3, start-stop systems multiplying engine wear. Every new automatic transmission vehicle now includes start-stop technology that kills your engine completely at red lights and restarts it automatically when you lift your foot from the brake pedal. Manufacturers proudly claim impressive fuel savings during city driving. What nobody advertises, honestly, is the catastrophic multiplication of engine wear events this technology creates. Consider the math with complete honesty. A traditional engine might accumulate 50,000 total start cycles over a 200,000-mile lifetime of normal use. A start-stop equipped engine operating in urban commuting traffic can experience that many individual starts in just 2 years of daily driving. Every single engine start creates what engineers call boundary lubrication. That critical moment when metal physically contacts metal before oil pressure fully establishes throughout the engine. Bearings, pistons, ring faces, and valve train components all experience their highest wear rates during these startup moments. Multiply startup cycles by 10 times or more, and cumulative wear accelerates proportionally. A fleet manager running 500 commercial vehicles tracked his maintenance costs meticulously over 5 years. Vehicles equipped with start-stop technology required 23% more starter, motor, and battery replacements than identical vehicles without the feature, completely erasing any theoretical fuel savings. Old engines started once per trip and ran continuously until you arrived at your destination. Simple, reliable, durable. Modern start-stop technology trades barely perceptible fuel savings for measurably shortened component lifespan across multiple expensive systems. Reason number 2, emission systems adding dozens of failure points. Modern engines must meet emission standards that would have seemed impossibly strict and technologically unachievable 30 years ago. Nobody argues against cleaner air for everyone, but achieving these stringent standards requires complex systems that add significant weight, mechanical complexity, and dozens of potential failure points that older, simpler engines never contained. EGR systems recirculate hot exhaust gases back into the intake manifold, introducing carbon deposits, corrosive soot, and moisture into areas specifically designed for clean filtered air only. Over 60,000 to 80,000 miles, EGR passages clog with hardite deposits. Intake manifolds cake with carbon residue. Throttle bodies gum up with contamination that simply wouldn't exist without the emission system. Diesel particulate filters capture soot that older diesels simply expelled harmlessly through the exhaust pipe. When regeneration cycles don't complete properly due to driving patterns, filters clog and create dangerous back pressure that damages turbochargers, reduces available power, and eventually requires $2,000 to $4,000 replacement. A comprehensive 2022 automotive repair industry survey found that emission control system repairs represented the single fastest growing category of service work nationwide, increasing an astonishing 340% over the previous decade. Each emission system serves genuine, important environmental purposes that benefit everyone. But each system also adds components that eventually fail, maintenance requirements that increase ownership costs significantly, and mechanical complexity that shortens practical engine lifespan compared to simpler designs that preceded them. Reason number 1. Planned obsolescence is absolutely real. Everything I've described in the previous 11 reasons leads directly to this final uncomfortable truth that no manufacturer will ever publicly admit, but every piece of evidence overwhelmingly confirms. Planned obsolescence isn't paranoid conspiracy theory. It's thoroughly documented corporate strategy that shapes every single engineering decision in modern automotive development. Manufacturers profit enormously when vehicles require replacement. They profit when repairs become expensive enough that purchasing new vehicles seems financially attractive by comparison. They profit when engines fail conveniently shortly after warranties expire, rather than lasting decades like the designs they deliberately replaced. Every thin timing chain, every extended oil change interval, every integrated component that can't be serviced separately, every turbocharger bolted to an economy engine. These decisions weren't made by engineers prioritizing your interests as a customer. They were made by finance departments calculating optimal replacement cycles that maximize what corporate strategists call lifetime customer value extraction. That Greek taxi driver achieved 2.9 million miles because he drove an engine designed before this philosophy dominated the entire automotive industry. His engine was designed by engineers measured solely by durability, built with materials chosen exclusively for longevity, and maintained on schedules designed for generational survival. Modern engines are designed by committees where engineering answers directly to finance, built with materials chosen primarily for cost reduction, and sold with maintenance schedules optimized for marketing appeal rather than actual engine protection. The old engines lasted longer because they were deliberately designed to last longer. Modern engines fail sooner because, let's finally say it with complete clarity, they're deliberately designed to fail sooner. 12 reasons why old engines outlast modern ones. From cast iron blocks built like bank vaults to planned obsolescence strategies specifically designed to empty your wallet repeatedly. The evidence is absolutely overwhelming. Engineering philosophy shifted permanently from building legends that last generations to manufacturing replacements that barely survive their warranties. Thank you sincerely for watching this entire video. I genuinely appreciate your time and attention. Comment your vehicle's make, model, and current mileage below. I'll tell you which of these 12 factors is most likely affecting your specific engine right now. That's not nostalgia talking. That's engineering reality finally exposed.